Again, what we're going to talk about today, how the book uses the term the coordinate plane. You know this is XY axis. Should all be familiar. It's nice if you have graph paper when you're doing this, but you don't on the board. You all should know how to graph a point. You have some point x, y. You start at the origin, you move over x, and you move up y, and there's your x, y point. X is positive here, negative here, y is positive here, here. You should know that we call this point of intersection, which is 0, 0, call that the origin. And this is a little arbitrary, but by convention, we call this quarter of the plane quadrant 1, and then we go counterclockwise, quadrant 2, quadrant 3, quadrant 4. We're going to let the noise pass. You know what that is? Budget that comes from giving people tickets for being in the way. Okay. Something that's, you don't have to pick it up right now, you will, especially as we get into trigonometry. There's something notable about these quadrants that is good to know, good to remember. The coordinates in the first quadrant are plus plus, they're both positive. In the second quadrant, your x becomes negative, so it's negative positive. Moving down, the third quadrant, both coordinates are minus, and then over in the fourth quadrant, it's positive, negative. This comes in convenient for various reasons. We're going to look at some functions that are going to follow this pattern. For example, there's a function that will be positive here, negative here, and positive here, because it has to do with first coordinate. There's another function that is going to be, we'll just say for the moment incorrectly, it's the product. So over here, positive, positive is going to be positive. Here, negative, negative, it will be positive. And the second and fourth, it will be negative. So positive times a negative is a negative. Okay, you should be really familiar with this. Not sure how this thing wants me to scroll yet. Okay, I'm going to reuse this here, and we're going to talk about for a second how would you graph a region on this, specifically the very simple region XY points, such that x is greater than or equal to 0. So this is going to include x equals 0, so the y-axis is where x equals 0, so I might want to mark this like this. And then I have to indicate all these points. When you're doing something with a computer, you can shade things. That's nice. You can't always do that. So again, here we have the first and the fourth quadrant are members of this graph. I know this stuff should be really simple and straightforward. That's why I'm going to try and go through fast. I know some of you are probably a little bored by this, but we'll get through this. We'll get to something more interesting in a few minutes. Okay. I might want to graph a line, specifically a horizontal line. That would be points x and y such that, well, y, we're just going to say 1 here. So we would pick some point at y equal 1, maybe another, and draw a line through it. When you know your graph is a line, and you're trying to just pencil and paper it, you only ever need 2 points. If you recall from your geometry class, how many points determine a line? It's just 2. Does anyone remember how many points you need to determine a circle? Geometry was a long time ago. Okay, if you have 3 points, there's just 1 circle that will go through them. All right. Another kind of regional graph here. If I wanted to show x and y such that the absolute value of y is less than 2, that is all points where y is between what? 2 and -2. So here, because I'm not using equal, I want to indicate that the line is not included. So the typical convention is to use a dashed line. So here's 2 and -2. Again, I have a dashed line. And then just something to indicate that all the points between these are included. So that's just another graph of a different kind of region. Right. So one of the things we may want to do with our graph is we might want to know the distance between 2 points. So if we have a graph, as before, and we pick 2 points we'll call A. We'll give A the coordinates x1 and y1. And another point B has coordinates x2 and y2. and we have a line segment between them. And we want to know what this distance is. So how are we going to find that? Well, we project these points over here, onto the axis. It's going to intercept here at y1 and y2. And using the distance for a line segment that we looked at before, we know this is the absolute value of y2 minus y1. Similarly, we can project these down onto the x-axis, where we'll intercept the coordinates x1 and x2. And we know this distance, again, is going to be the absolute value of x2 minus x1. But because these are all parallel and perpendicular lines, I can also say that this is x2 minus x1, absolute value, and this is y2 minus y1. These are the two sides of this triangle. This is a right triangle, so what famous formula are we going to use?
Pythagorean theorem.
Thank you, Pythagorean theorem. The Pythagorean theorem is going to tell me that the sum of the squares of the sides is going to be equal to the square of this distance. So let's just call this distance A comma B for the moment.
Thank you.
So we know that distance A comma B squared, that's my C squared, and A squared plus B squared equals C squared. My A squared could be absolute value of y2 minus y1 squared. And finally, absolute value of x2 minus x1 squared. Well, let's solve for this. So the distance from A to B is just square root. And now, since we're squaring, we don't really need the absolute value signs, right? Absolute value is going to turn a negative into a positive, but squaring will do the same thing, so it's redundant. So this becomes our formula for the distance given the coordinates x1, y1, x2, y2. This gives us the formula for the distance between 2 points. All right, so let's do a simple example. Let's just say, what is the distance between, say, 5 comma 7 and 2 comma 3? Where would that be? I'm just going to make up some scales here. 1, 3, 4, 5, 6, 7, 8. 6. Not perfectly drawn, but 2, 4, 5, 4, 6, 7. All right, that's the first point, and 2, 3. So I want to find this distance, and I can just plug this into my formula. So y2 minus y1, that's, I guess, 3 minus 7 minus 4. But squared is 16, and 2 minus 5 is minus 3, squared is 9, so that's square root of 25, which of course is 5. we could do something a little more complicated than that. We could ask a question. We could say, well, if I have 3 points, A at 1, -2, B at 8, 9, and C at 5, 3, we could say, which of A and B is closer to C? That would be a pretty straightforward question. Well, to answer, we need to find the distance between we need to find the distance AC and BC. So let's go ahead and do that. Distance AC is just, again, using this formula. 3 minus 2 is 5 squared is 25. 5 minus 1 squared is 4 squared is 16. So this is just the square root of 41. And then my distance BC, again, same kind of calculation. 9 minus 2, 9 minus 2, so 9 plus 2 is 11. Is that right? No, I'm sorry. I want C and D, excuse me. 3 minus 9, that's minus 6. Squared is 36. And 5 minus 8 minus 3 squared is 9. So that's the square root of 45. So which one is closer? A or B? It's A, right? Square root of 41 has to be less than the square root of 45. Okay. So I think I want to leave this up here. This is our distance formula. And I'm going to introduce a new formula. Is the distance. Next formula is going to be the midpoint formula between A at x1, y1 and B at x2, y2. So the midpoint of A and B is just going to be the point with the coordinates x1 plus x2 over 2, the average of the two, and y1 plus y2 over 2, the average of those 2 points. Now, I just pulled that out of my hat. Let's just take a look here. So if I have A over here at x1, y1, and B at x2, y2. I'm claiming that this point in the middle, the midpoint, is x1 plus x2 over 2, y1 minus y1 plus y2 over 2. Let me show you that that has to be the midpoint using the distance formula. Let's look at this distance AM using the distance formula. That would be x1 minus x1 plus x2 over 2 squared plus y1 minus y1 plus y2 over 2 squared square root. That's what the distance formula tells me the distance between A and M is. So let's simplify this a little. This is x1 minus x2 2 squared plus y1 minus y2 over 2 squared. I did that kind of fast. I just put x1 over the common denominator 2, so that's 2x1. I subtract this, so the x1 goes away, and I've got a negative x2. So same thing with y. All right, let me do the same thing over here between b and m. So now I have square root of x2 minus x1 plus x2 over 2 squared plus y2 minus y1 plus y2 over 2 squared. Well, that looks a little different. x2 minus x1 over 2 squared plus y2 minus y1 over 2 squared, but clearly x1 minus x2 squared and x2 minus x1 squared is the same thing. So that tells me that this point is equidistant between these. It doesn't actually show that it's the midpoint. Right? It could be some other point. It just happens to be equidistant. So what we really want to do is we want to say, well, what's the distance between A and B? Because if this distance and this distance are half of that, then it has to be the midpoint, right? So what is the distance between A and B? Well, it's just square root of x2 minus x1 squared plus y2 minus y1 squared. If you think about it, squaring the 2 here, right? Here, so their common denominator is 4. Under the radical, you take it out of the radical, this is just half of this. So clearly m is the midpoint. Questions or okay. Well, let's do an example. So let's start with a simple example. What's the midpoint between 9, 3 and negative 3, 5? Well, we just plug this into our formula. 9 plus negative 3 over 2, and 3 plus 5 over 2. So this is 3, and this is 4, and that's my midpoint. Couldn't be too much easier, could it? Okay, I'm sure the answer is no, but is there anyone here who didn't take geometry in high school? Good. All right. I'm interested to know if anyone remembers a theorem. Theorem goes like this. You have a parallelogram. Anyone remember parallelograms? Two sides parallel. Opposite sides are equal. Opposite angles are equal. Okay, so there's a theorem that says the diagonals of a parallelogram bisect each other. Actually, it's an if and only if theorem. If you have a parallelogram, the diagonals bisect each other. But if you have a quadrilateral, and its diagonals bisect each other, it's a parallelogram. So we're going to use that. We're going to look at some points. And 4, 4. Let's just do a little graph so we know that we're at least in the ballpark here. So 1, 2, 7, 5, 9, and 4. So it might be a parallelogram. It's not something crazy. So we want to check where's the midpoint of these two and where's the midpoint of these two. Because if it's the same point, we know we have a parallelogram. Okay. So explaining it was much harder than doing it, right? We'll just take 1 plus 5 over 2 and 2 plus 9 over 2. That's the midpoint of these two. And then we look at 2 plus 4 over 2 and 7 plus 4 over 2. That's the midpoint of these two. This is 3 and 11 halves. This is 3 and magically 11 halves. So now we have an easy way. We have 4 points to see do we have a parallelogram. Here's the picture of that. Okay. All right, let's talk about something hopefully everyone's fairly familiar with, graphing a line. So let's take an equation of a line here, a linear equation. So the book goes out of the way to say, well, you could have a whole table of points, and you can graph each of those points. But really, we only need 2 points, right? 2 points to determine a line. So let's try and find some easy points to graph. Let's say x is 0. It's always easy to compute with 0. So if this is 0, then y is -3. And again, I'm going to set y equal to 0. 2x equals 3, so x is 2 halves. So now I have 2 points. So let's give them a try. 0 in the x direction, -3 in the y direction. 3 halves, so about here, and then 0. My best artistic impression of a straight line. Okay, so that's pretty easy. In particular, these points are called the intercepts. Intercepts. An intercept, when you have a graph of a curve, wherever that curve goes through 0 is an intercept. So with a line, often will have, this is the y-intercept, which I hope you're all familiar with. We'll go over this a little more. You don't use the x-intercept as much, but that's an intercept. You don't necessarily have both intercepts. I guess that's not part of today, is it? You could have a horizontal line, so that's only going to have a y-intercept. Or you can have a vertical line that only has an x-intercept. Okay, we're going to do more with graphing of lines, obviously, but that's all for today, I think. Right. Let's look at graphing an absolute value function. Now, use the word ahead of when I allow. No one here heard the word function. What's next week? Absolute value equation. Y equals absolute value of x minus 2. So, the thing to note, it looks a lot like a linear equation. It'll act a lot like a linear equation, but something happens where inside the absolute value you get 0. Again, this is what I would call a critical point. X equals 2, because it's where the direction of the line is going to change. So when you're graphing an absolute value, you want to know where this point is. It's at 2, 0. So let's start our graph. Critical point. So from here, we're going to need a couple more points. So what would be a good choice? Well, again, we could try 0. Well, 0 minus 2 is minus 2, but the absolute value is 2. And what else would be a good point to try? Well, let's try kind of the point on the other side of it. Let's try 4. So 4 minus 2 is 2. Absolute value of 2 is 2. So now I have 2 more points. So let's plot those. 0, 1, 2. Okay. That's going to be one ray coming off of this graph. And then 4, 1, 2, 3, 4, 2. It's going to be the other ray. As you look at this, one thing you might want to note is that because y is just absolute value of something, it's always positive, and if you look at this graph, you can see right away that all y's are above the axis. So that makes sense. So that's graphing an absolute value equation. Find the critical point, and then choose another set of points to find out where it goes off to. one step more complicated. We're now going to graph a second degree equation, or in this case it's going to be a parabola. So my parabola is y equals x squared minus 4. And to make things easy, I want to factor this. See, it's my pattern x plus y, x squared minus y squared, b squared minus b squared, x plus 2, x minus 2. And to do this, you have to kind of know already what a parabola looks like. I think we all have some idea. And I'm going to use that same strategy of finding the intercepts. So if I set y equal to 0, and I say, all right, well, where is y equal to 0?
On the y-axis?
Y is 0 on the x-axis, right? Whereas if y could be on the it could be on the y-axis at 2, but that's, wait a minute, I'm sorry. I think you're right. That's what the y-intercept is, where it crosses the y-axis. So again, my question is, where in this equation, how do we get y equal to 0? What values of x? Yes?
Negative 2 and positive 2?
Speak up.
Negative 2 and positive 2?
Negative 2 and positive 2. We have 2 of them. All right. That's pretty good. Turns out parabolas are like circles in that you need 3 points to determine a parabola. So we might as well go for the x-intercept. I'm sorry, the y-intercept. Backwards in my head. So what happens when I plug in 0? What do I get?
-4.
Take another look. Unless I misheard you. I heard -1.
-4.
-4, okay. All right, so now we have 3 points. That should be enough. 1, 0, 1, 2, 3, 4. That's this point here. 2, 0. Intercept. Another. Okay, well that's enough. Here's my parabola. Considering digressing for a minute. Parabolas are kind of cool mathematical objects. Has anyone here ever looked through a telescope? Anyone look through a telescope with a mirror? Okay. Do you know what the shape of the mirror was? It's a parabola, except spun around the axis. Right? The reason is because parabolas have this magic property that if light is coming straight down, all the light gets reflected to one point. Obviously here. We'll also see this if anybody a photographer here, right, uses a flash, and the flash has a little dish. The dish has a shape, and it's a parabolic reflector. just the opposite. You get the little light bulb here, and all the light kind of goes out parallel. So that's a neat thing about a parabola. Another thing that's neat about a parabola is if you're really, really like close to, this point here, we expand this. It kind of looks like a circle. It's very, very close to a circle. And it turns out if you want to make a telescope, it's really hard to make a parabola, but it's really easy to make a circle or a sphere. So that's actually what you do. You make a sphere really close to your parabola, and then you just fix it a little, make it a parabola, because there's not much difference. Difference is like when you're dealing with a telescope error between the circle and the parabola, it's like 1/1,000,000th of an inch. So it's pretty close. Okay. Digression on parabolas that you'll only need in your future career as an astronomer, if you happen to have one. Next thing we're going to look at is graph of a circle. So you'll find when we're graphing circles as a convention, we often call the center of the circle, we give it a name HK if we don't actually know the coordinates. And if you have a circle, you know that you have a radius, and that the circle will be all these points x, y, whose distance between each of these points x, y is r. Well, that gives us a hint as to what the equation of a circle looks like. Using our distance formula, we could just say x minus h squared plus y minus k squared square root equals r. The problem with the equation, the way it is here, is this would just be the equation of the top of the circle, because this is always positive. But to get the entire circle, we can square both sides, right? So either the positive square root here or the negative, right, will work. And we get x minus h squared plus y minus k squared equals r squared. So I guess that deserves to be put over here for now. Equation of the circle. Again, where h and k are the same. All right. Let's do an example problem. Find the equation of a circle with a center at 2, -5 and radius 3. We just plug in, right? We have x minus 2 squared plus y minus negative 5 squared, well that's plus 5 squared equals r squared, 3 squared, or 9. So that couldn't be much easier. Right. And now let's look at graphing problem. We have an equation x squared plus y squared equals 25. We want to graph that. So we want to know where the center is and what the radius is. Well, this is of course x minus 0 squared plus y minus 0 squared. And the square root of 25 is 5, so the radius is 5. Equation is 5 squared. So all we have to do to graph this is put our center at the origin and have our circle I once read that one of the tests of it, they used to test the artistic talents of people by asking them to draw a circle by hand. As you can see, I don't qualify, but okay. We're just zooming through stuff here. Is everybody okay? All right.
Is that the preferred method to, like, have it down on paper, the standard form? Is that the way you want it, usually?
Well, you could, with an equation like this, you could skip a step. You could just say, obviously, it's at 0, 0, and obviously the radius is 25. But what if I gave you an equation like this, like x squared plus 2x plus y squared plus 4x plus, minus 18 equals 0. You go, and I said, I want you to graph that. Well, you might have some intuition that there's a circle in there, right? But you have to dig it out. You'd have to complete the square. So here you say x squared plus 2x plus 1 plus y squared plus 4x plus 4. And then we'll move the 18 over, and we'll have to add back the 1 and the 4. And we'll get x plus 1 squared plus y plus 2 squared. You see, it could be useful to put it into that form, right? Equals 23, or square root of 23 squared. And now that it's in that form, I can see right away the center is at minus 1, minus 2. Its radius is square root of 23. Is that more than you wanted, or?
No, that's great. But if you email me that, I would send you back like a GIF of like the 1920s, somebody jumping out of the building in 5 seconds.
A weird song just popped into my head about the crash of 29, but all right. Okay, what else could we do with this? What other tracks lying wait in the homework for you? What about a question like this? Okay. 1 and 8, 1, 8, and 5 minus 6 are points on the diameter of a circle. They're on a circle, and they're also on the diameter. So, kind of rough picture, I don't really know where they are. I've got 2 points here, say A and B. These are my A and B. Do I have enough information to figure out the equation of this circle? Well, first thing I want to know is where's the center of the circle? How would I find the center of the circle? Okay. So 1 plus 5 over 2 and 8 plus minus 6 over 2. So that's 3 and that's 1. Okay, I've got my center. Good. Because now I know it's going to be x minus 3 squared plus y minus 1 squared equals r squared. But I still need to know r. Can I find r? Well, that's just the distance from the center to either of these points. Or if you want, you could find the distance between the points and divide by 2. I think I'm going to try that. Okay, so 1 minus 5 squared, square root, plus 8 minus 6, 8 minus 6, is plus squared. So this is 4 squared, or 16, and this is 14. Did I do that right? I think I did it wrong. No, I did it right in my notes. Okay. Anyone know what 14 squared is? I run out of steam at 13. I know that one. 14 squared. Is it good to know? 169. 15 squared is 25. I don't know this one. I'm cheating. 196. Oh, but I want half, right? So this turns out to be the square root of 212 over 2. But I can divide 212 by 4, right? And I get the square root of 53. So square root of 53 squared. So now I know my circle is at 3, 1, and its radius is square root of 53. Okay. Last subject we're going to look at today is symmetry. We're going to, when we look at equations and graphs and things in this class, a lot of times we're going to find symmetry is really helpful. Let's look back at one of our parabola equations. Y equals x squared. It starts at the origin and looks like this. And you can see that for any point here, x, whatever the y is, that's x squared. If there's a point opposite negative x, well, negative x squared is x squared. Right? That's where symmetry comes from. So this is symmetry around the y-axis. And in general, if you can substitute for x minus x, and you get the same equation, you have that symmetry. Similarly, if I had an equation x equals y squared, which is going to look like this, if I can substitute for y, negative y, let's do that. X equals negative y squared. Well, that's just y squared, that's the same. So now I have symmetry around the x-axis. Well, finally, we might come across something like y equals x cubed, which, if you're not familiar, kind of looks like this. It looks a little like a parabola on one side, but then goes off in the other direction. And you can see, if I substitute for x minus x, this will become y equals minus x cubed. That's not the same. If I substitute, I have 3 minutes. Thanks. If I substitute minus y, it's different. But if I substitute both x and y as minus x and minus y, what do I get here? Minus y equals minus x cubed is minus x cubed. But I can multiply through by -1, and I get my equation back. Okay, this is symmetry around the origin. For each point over here, there's a similar point here.
Is there like a rule of thumb to go off of with evens and odds? I remember thinking
Yes,
about that.
yes. I'm going to suggest you keep that in mind. It will come back. We'll talk about even functions and odd functions. Yeah. So, quick problem. Very quick problem because I only have 60 seconds. If I look at y equals x cubed minus 9x, and I say, what kind of symmetry does that have?
Origin.
Okay, we'll give that a try. Minus y equals minus x cubed. Oh, this is plus 9x, right? Because of the minus. But if I multiply through by -1, I get x cubed minus 9x. So I know that this is going to have symmetry around here. Okay, thank you. See you Monday.